thanks for the invitation. I will be talking about the XOR Ising model and the constraint percolation. Okay, so I'm sure everyone's familiar with the Ising model. So we have a graph, and each vertex associates a random variable. The random variable can take two possible values, either spin up or spin down, or we can also consider this spin up will associate a numerical value plus, and the spin down will associate a numerical value negative. And then we have a plus or negative configuration of vertices of this graph. And for each configuration, we assign a probability. Then we have a probability measure whose sample space is a set of all the configurations. Okay, and then this probability measure depends on parameter, usually the temperature. And as the graph becomes larger and larger, we are interested in the phase transition when we change the temperature. When we change the temperature, if we can observe a phase transition, or if there's some critical behavior. I'm not going to the details of the phase transition of the Ising model, but what I'm going to talk about is something called the XOR Ising model, which is also on a graph. Each lattice is associated random variable, which could take two possible values, either plus or negative. So the XOR Ising model. So the XOR Ising spin, the random variable associated to each vertex, is the product of two independent, identically distributed Ising spins. So it's become an interesting model to work on because there is a conjecture by David Wilson about XOR Ising model, which says that the contours of critical XOR Ising model converges to the sorry.
You don't have to feel bad.
I don't know. Okay, so the conjecture is we also consider those contours separating separating vertices with different configurations. So those contours, the conjecture is those contours are conformally invariant in the scaling limit and converges to CLE4. Then a first step towards this conjecture was done by Dithelier and Boutelier. They show that the contours of the XOR Ising model has the same distribution as the level lines of the diagonal height functions on the square octagon lattice. So what I'm going to do is I'm going to focus on the percolation property of the XOR Ising model. So what is the percolation property of the XOR Ising model? Basically, we are asking classical questions for the XOR Ising model, whether or not there exists an infinite connected set of vertices such that each vertex has a configuration plus, or there exists an infinite connected set of vertices such that every vertex has a configuration negative. Okay, so in order to answer these questions, what we are going to do is we are going to introduce a more general model, which is called a constraint percolation model. So those are percolation models on a graph Z2. So this is so the graph is just the regular square grid, two-dimensional, and we will color the faces by black and white such that faces of different color share an edge, and faces of the same color cannot share an edge. Then the set percolation configuration space is just each vertex can freely take the value 0, 1, and then we are going to impose some constraint on the set percolation configuration space. So the constraint is around each black face there are 4 vertices. So if we just consider those 4 vertices can freely take the value 0, 1, there are 16 possible total configurations, but the constraint is around each black face. Either all the 4 vertices have the same configuration, all of them have the state 0, all of them have the state 1. Or we use a vertical line to divide those square, each black face into 2 parts, the left part and the right part. So the left part, 2 vertices have the same configuration. The right part, the 2 vertices have the same configuration. or we use a horizontal line to divide the black face into two parts, the two vertices above and two vertices below. And two vertices above have the same configuration, and two vertices below have the same configuration. So these are all the 6 allowed possible configurations among the 16 possible configurations. Okay, and examples of the constraint percolation. So there are a lot of examples of constraint percolation. So those are just some special constraint we impose. And there are other examples like perfect matching. So if we consider those perfect matching as a bound percolation model, so each edge can freely take the value 0 or 1. And then the constraint is each vertex has exactly one incident present edge. And the polygon model can be considered as a bound percolation model with some constraint. So each edge freely takes the value 0 or 1, but the constraint is each vertex has an even number of present edges taking value 1. And 6-way model, so on a degree 4 graph and give each edge an orientation, satisfy the constraint that each vertex has exactly 2 incoming edges and 2 outgoing edges. So here is a bigger picture about the constraint percolation model on the square grid. So we can say there are 2 different states, and we are also going to consider those boundaries separating different states. So in order to consider those boundaries separating different states, we are going to introduce 2 auxiliary lattices, L1 and L2. So both L1 and L2 are square grid of cell length 2. So they are dual lattices to each other. And so both of them have vertices located on centers of white faces. So we can say the edges. So given this constraint, we can say that the edges of L1 and L2 could be edges separating vertices of different states. Then we're going to consider probability measures on the set of all constraint percolation configurations. Those probability measures will impose some natural assumptions. First of all, we assume those probability measures are 2Z cross 2Z translation invariant. That means if we have an event, and for any configuration in this event, and then we translate this event by a group element into Z cross 2Z, we obtain a new event. This new event has the same probability with the original event. Then we say this probability measure is 2Z cross 2Z translation invariant. And we also assume that it is 2Z cross 2Z ergodic. So if we have an event, and it is 2Z cross 2Z translation invariant, that means for each configuration, we multiply that by a group member into Z cross 2Z, and we get a new event. This new event is the same as the original event. That means that the event is 2Z cross 2Z invariant. If any 2Z cross 2Z translation invariant event has probability either 0 or 1, and then we say this probability measure is 2Z cross 2Z ergodic. And we also have further assumptions. So for example, the strong translation invariant, if we have a subgroup of Z cross Z generated by 1, 1, and 1, negative 1. So this H is subgroup of Z cross Z, but 2Z cross 2Z is a subgroup of this H. So this is actually a stronger translation invariant assumption. Basically, if this probability measure is H translation invariant, then it must be 2Z cross 2Z translation invariant. And also we assume this measure is symmetric under interchanging of state 0 and state 1. Okay, so those are all the assumptions. So we define the cluster and contour in a natural way. So cluster is nothing but a maximal connected set of vertices in which every vertex has the same state. So we could have a 0 cluster or 1 cluster. So 0 cluster is a connected set of vertices. Every vertex has state 0, and 1 cluster is a connected set of vertices. Every vertex has state 1. Okay, so we can also have example of contours. So contour is just a connected set of L1 edges or L2 edges such that each edge is separating vertices of different states. So a point worth noticing here is that given this special constraint, if we consider those edges of L1 and L2 to be present if it separates vertices of different states, absent if it doesn't separate vertices of different states, and those present edges of L1 and present edges of L2 cannot cross each other. So present edges of L1 and present edges of L2 cannot cross each other, and then as a result, each connected component of present edges, so each contour must be either an L1 contour or an L2 contour. Because we cannot have a connected set of present edges which has both L1 edges and L2 edges given that constraint. So this is an important fact and will be used in the proof later on. So then we're going to ask natural questions for classical questions in the percolation. For example, is there an infinite 1 cluster or is there an infinite 0 cluster? And another question is there an infinite contour? So for example, so those questions has been studied extensively in the non-constraint case. So when there's no constraint, so you consider i.i.d. Bernoulli bound percolation on the square grid. So for the i.i.d. bound percolation, so each edge is associated with a Bernoulli random variable which has probability to take value 1, the probability p to take value 1 and probability 1 minus p to take the value 0. So it is known that there is a critical value pc. When p is less than pc, then almost surely there are no infinite clusters, and p is greater than pc, almost surely there exists exactly one infinite cluster. Then the question is what happens at pc. So this turns out to be a hard problem, and for the square grid, i.i.d. critical Bernoulli bound percolation, it is proved that there are no infinite clusters. And for the higher dimensional cubic lattice, for example, when the dimension is greater than or equal to 19, so it is proved that the i.i.d. critical Bernoulli bound percolation has no infinite clusters. And this result recently has been extended to the dimension d is greater than or equal to 11. Okay, so however, when d is equal to 3, so we consider a 3-dimensional cubic lattice, we ask as a criticality whether or not there exists an infinite cluster or not. So this is still an open question and turns out to be an open question for a long time. And on the other hand, for the non-amenable graph, that means for a graph we consider it finite subgraph. We consider a finite subgraph, and remove that finite subgraph, we count the total number of infinite clusters. And then we compute the inframe over all such finite graphs. And the total number of infinite clusters, so what is a non-amenable group? I'm sure lots of you have already known. So we consider a finite graph, and the removal that finite graph, we consider a finite graph, finite subgraph, and then the number of vertices on the boundary of the finite subgraph, and divide the total number of vertices on this graph, and we compute the supreme of this quotient over all the finite graph. If this supreme is strictly positive, then this graph is called non-amenable. If the supreme is 0, then this graph is called amenable. In particular, all the cubic lattices embedded into the finite dimensional Euclidean plane, they are amenable graphs. So, however, on the non-amenable graph, it could be proved that critical i.i.d. bounded set percolation on any non-amenable graph has no infinite clusters. Okay, and yeah, so any non-amenable group, and we construct a Cayley graph from that group. This is a vertex transitive amenable graph. So then we consider, so the same question has also been discussed for the dependent percolation. For example, the Ising model is not Bernoulli i.i.d. independent. So for the two-dimensional ferromagnetic Ising model, in the critical case, there are no infinite plus clusters and no infinite negative clusters. Okay, so so the main theorem I'm going to discuss is the similar question, the percolation question when we impose the constraint as discussed, as defined before. So we consider a probability measure on the constraint percolation state place, satisfying all those conditions like translation invariant, strong translation invariant, and ergodicity, and also symmetric under interchanging 0 and 1s. Let's consider A to be the event that there exists unique infinite cluster consisting of 1s. Then the probability of that event is equal to 0. So so in this theorem, we make no assumption of stochastic monotonicity or FKG inequality. So in particular, in the i.i.d. Bernoulli case or the ferromagnetic Ising case, they all satisfy the stochastic monotonicity or FKG inequality. But in the constraint percolation case, in general, these conditions does not hold. However, even if without these conditions, we can still prove the non-existence of unique infinite one cluster. So let me briefly.
Can you remind us what the conditions 1 through 4 are? And are we on this?
So
Square grid still, right?
So it's just a translation invariant, strong translation invariant. So translation invariant by a subgroup of z cross z generated by 1, 1, and 1 negative 1, and ergodic. Any 2z cross 2z translation invariant event has probability 0 or 1, and symmetric. It is symmetric. The probability measure is symmetric in interchanging 0 or 1. Okay, so those are natural assumptions. So first of all, let's say so this is because of ergodicity. So there exists a unique infinite cluster consisting of 1s, and we translate it by a group member into z cross 2z, and then there's still an infinite cluster consisting of 1. So this is translation invariant event. Therefore, by ergodicity, either this event has probability 0 or it has probability 1. But because we want to show this event has probability 0, then we want to exclude the case it has probability 1. What we're going to do is we just assume that it has probability 1, and then we will obtain a contradiction. So then we just consider A prime to be the event that there exists a unique infinite cluster such that every vertex in that cluster has state 0, and then the probability A is equal to probability A prime, and then assume that the probability A is equal to 1. Then we can consider probability A intersection A prime is equal to 1. Okay, and then let's consider. So we assume this, and we're going to obtain a contradiction because this mu A is equal to mu A prime. So mu A prime is equal to 1 if mu A is equal to 1. So their intersection is 1 as well. Then let's consider B1 to be the event that there exists infinite L1 contour. And B2 is the event that there exists an L2 contour. So assume this contour is incident to both the infinite 0 cluster and infinite 1 cluster. Then we have the intersection A and A prime is equal to 1 implies that the union of B1 and B2 is equal to 1. So because we have two infinite clusters, we must have infinite contour separating them. This infinite contour is either an infinite L1 contour or an infinite L2 contour. Okay, so and then mu B1 equals mu B2 is by strong translation invariant, because if we have an L1 contour, we translate it by a group by 1 negative 1, and we translate that contour onto the dual graph. We obtain a infinite L2 contour. So mu B1 is equal to mu B2. Okay, and then Because of the ergodicity, either mu b1 equals mu b2 equals 0 or mu b1 equals mu b2 equals 1, because they are both translation invariant event. In particular, they are translation invariant under 2z equals 2z. So for an L1 contour we translated by 2z equals 2z, we again get an L1 contour. Okay, so then from mu b1 union b2 equals 1, we actually obtain that mu b1 intersection b2 intersection a prime is equal to 1. Then we have such an interesting picture. So we have an infinite 0 cluster here, and infinite 1 cluster here, and we have an infinite C1 contour incident to both the infinite 0 cluster and infinite 1 cluster. And we have a C2 contour incident to both the infinite 0 cluster and the infinite 1 cluster. And this C1 contour and C2 contour cannot intersect each other. Then somehow we can find a path here, just closest path to this infinite C1 contour, just surrounding this. And this path, it does not cross any contour at all. Therefore, any vertex on this contour must have the same state. But this is contradiction because starting from here, it has state 1, but ending at here, it has state, starting from here, it has state 0, and ending at here, it has state 1. So this is a contradiction. This contradiction actually implies that the assumption is not correct. So the probability that there exists a unique infinite 1 cluster is equal to 0. Okay. So we prove this result for the constraint percolation. Then natural question to ask is how about the unconstrained case? So if we have probability measure satisfy all those conditions like translation invariant, ergodicity, and symmetric under interchanging of 0 and 1s. So is it true that there is an that the theorem holds for unconstrained percolation as well? That means, can we prove that almost surely it's not possible that there exists a unique infinite 1 cluster? So the answer is no. Let's say an example. So we consider xm and x1 are two independent sequences of i.i.d. Bernoulli random variables. Okay, so we consider two independent sequences of i.i.d. Bernoulli random variables. So this x1, x0, x negative 1, and okay, and y0, y negative 1, y negative 2, and okay. So there are sequences of i.i.d. Bernoulli random variables. Each random variable takes value 0 with probability 1/2 and take value 1 with probability 1/2. We consider a run of xy is a maximal non-empty set. So we have 0, 1, 0, 0, 1, 1, 1. So a run is a maximal connected set. Run is a maximal connected set. Maximum connected set of digits such that every digit has the same have the same state. So similarly for y, we have the definition of those runs. So it's a maximal connected set of digits such that every digit has the same state. So a set rectangle. So a run rectangle is a rectangle I-cross-J such that I is a run of xm and j is a run of yn. So a set rectangle is a rectangle. So both x, y are runs of 1s. Okay, And the bound rectangle is a rectangle such that exactly one of the interval is round 1 and the other interval is round 0. Then we can place a vertex at each side rectangle and place an edge at each bound rectangle. Then we get a random graph. This random graph is isomorphic to the two-dimensional square grid. Then for this random graph G, and we consider a uniform spanning tree of this random graph. Then assign each vertex of the original graph value 1 if it lies in the uniform spanning tree. Assign it value 0 if it does not lie in this uniform spanning tree. And then this new percolation model is satisfy all those conditions: translation invariant, ergodic, and also symmetric under interchanging of 0 and 1s. But almost surely in this new configuration model, there's a unique infinite one cluster. So that shows that if we don't have such a constraint, and we cannot get the conclusion that the probability that there exists unique infinite cluster has probability 0. Then another question is, if we have the constraint model, and you have a question?
Yeah, can you define this? What's the point of the spanning tree?
The spanning tree, because it's spanning, and then it's a tree, it's connected. So then there is unique infinite cluster, right? So on this spanning tree, every vertex of original graph lies on this spanning tree has state 1. Otherwise, it has state 0, and it has unique infinite cluster. It makes sure there's a unique infinite one cluster.
By cluster, you have to add connections from along the edges of the spanning tree. Is that what's going on?
Yes. So for example, you have such a so you just consider this square, and you have a spanning tree like this. And every vertex here, every vertex in this box is 1, and every vertex in this. There are 1s. There are 1s. So there are 1, 1, 1. But everything not on this tree, these are zeros. So once you have such a spanning tree, this tree is spanning. It has only one connected component, so there's a unique infinite one cluster. But the spanning tree obviously is translation invariant, and it's mixing, and therefore it's ergodic. It's an ergodic measure, and also it's translation invariant. It's symmetric with respect to interchanging of 0 and 1s, because you consider the dual graph is still a spanning tree. Because you just consider, the dual graph is also a spanning tree. Then another question we can ask is, given those probability measures satisfying assumptions 1 through 4, and is it possible that there exists more than one infinite one clusters? And the answer is yes. Okay, so for example, we just consider so on Z2, each row you identically assigns either all of them zeros or all of them 1s. So each row, either all of them zeros or all of them 1s. So for each row, you either assign all of them zeros and all of them 1s. Okay, both with probability 1/2. Then this way you have a constraint measure, a measure on the constraint sample space. And then its translation invariant is ergodic, and it's symmetric with respect to exchanging 0 and 1s. However, in this case, almost sure there are infinitely many infinite 0 clusters and infinitely many infinite 1 clusters. So those given condition 1 through 4, we cannot exclude the case of infinite many infinite 0 clusters and infinite many infinite 1 clusters. And in order to exclude that case, what we're going to do is we're going to introduce a new assumption called finite energy. So what is the finite energy assumption? Basically, we consider the marginal distribution of the L1 contours and L2 contours, and for each phase, And what we are going to do is we are going to change every present edge to absent and change every absent edge to present. So for each single phase, if we do that, for each fixed single phase, if we just do that for one single phase, for any event, before we do that, if this event has strictly positive probability, then after we do that, this event also has strictly positive probability. This is called the finite energy. So if the finite energy, if we further assume the finite energy assumption, we assume it's weak translation invariant, weak ergodic, and finite energy, and we can show that in a constraint percolation model, there's at most one infinite L1 contour, at most one infinite L1 contour. Okay, so why is that? First of all, let's define the number of ends. So a number of ends of finite graph. So we have a finite graph and remove the number of ends of infinite graph. So we have a finite graph. We remove an infinite subgraph and count total number of infinite components after removing this finite subgraph. And then we compute the supreme over all such finite graphs. And then this number is the number of ends. In particular, if we have the two-dimensional square grid or hexagon lattice or triangle lattice, anything like that is a graph of one end. It's a graph of one end. And if we consider a regular tree, like its degree is greater than equal to 3, it's a graph of infinitely many ends. And if we consider a straight line, it is a graph of just a tree of degree 2, it's a graph of 2 ends. Okay, so, and then there's theorem saying that for invariant percolation on amenable graphs, any infinite cluster has at most 2 ends. Then if there exists more than one infinite L1 contour, then if there exists more than one infinite L1 contour, and somehow we can change the configurations on a finite, if there exists more than one infinite L1 contour, by finite energy, somehow we can change the configuration on a finite box such that after changing configurations on this finite box, we can somehow merge those multiple L1 contours into one L1 contour, and this L1 contour has more than 2 ends. So by this contradiction, we can show that almost surely there's at most one infinite L1 contour. And then combining all the results we have, if we have a probability measure on the constraint configuration sample space, satisfying all those assumptions, then almost surely there are no infinite contours, and almost surely there are no infinite clusters. Okay, first of all, by just the previous theorem, there's at most one infinite L1 contour, and at most one infinite L2 contour. And B1 is the event that there exists exactly one infinite L1 contour, and B2 is the event that there exists exactly one L2 contour. And because of the strong translation invariant, and B1, B2 must have the same probability to occur. And then either both of them have the probability 0 or both of them have the probability 1. This is by ergodicity. And A0 is the event that there is an infinite 0 cluster, and A1 is the event that there is an infinite 1 cluster. A0, there is an infinite 0 cluster incident to both the infinite L1 contour and the infinite L2 contour. And A1 is the event that there is the infinite 1 cluster incident both to the infinite L1 contour and infinite L2 contour. So if we want to show that mu B1 equals mu B2 equals 0, we only need to show that mu B1 is equals mu B2 equals 1 leads to a contradiction. So what we're going to do is we're going to provide by contradiction, if we assume that mu B1 equals mu B2 equals 1, then there is an infinite cluster incident to both the infinite L1 contour and the infinite L2 contour. Okay, then because there are 2 infinite cluster contours, then there must be an infinite cluster separating them. So this infinite cluster can either be an infinite 0 cluster or an infinite 1 cluster. So we have mu A0 equals mu A1 equals 1 because the ergodicity and the symmetry and translation invariant. Okay, then again we get those. We obtain mu A0 intersection A1 intersection B1 intersection B2 is equal to 1, and again we obtain such a picture, and we can obtain a contradiction. So recall that we have already shown that this is not possible. The proof is based on the specific geometric property of two-dimensional plane. So therefore, same argument applies, and we obtain a contradiction. So why we are interested in this specific constraint for the percolation? Because this is related to the percolation properties of the XOR Ising model. So we consider sigma 1 and sigma 2 are two i.i.d. Ising spins. So both of them have same coupling constant, and both of them are under periodic boundary conditions. That means we obtain an infinite volume Gibbs measure by using a larger and larger torus to approximate the two-dimensional plane. And we assume both sigma 1 and sigma 2 are critical. So then we have the theorem for the critical XOR Ising model. Almost surely there are no infinite plus clusters, and almost surely there are no infinite negative clusters. And almost surely there are no infinite contours. So why is that? Okay, we can also obtain results on non-critical XOR Ising model. So for the high temperature XOR Ising model, we define that. So recall that XOR Ising spin is the product of two i.i.d. Ising spins. If both Ising model are high temperature Ising model, and we say that the XOR Ising model is high temperature. So in particular, if the coupling constant satisfies this condition, and then each sigma 1 and each one of sigma 1 and sigma 2 is in a high temperature state, and we define that the product XOR Ising model is also in a high temperature state. And similarly, if the coupling constant of both sigma 1 and sigma 2 satisfy this condition, and then the Ising model is both sigma 1 and sigma 2 are in the low temperature state, and then therefore the XOR Ising model we define it to be in the low temperature state. Okay, so the contours in the XOR Ising model has the same distribution as level lines or diagonal height functions on the square octagon lattice. Okay, so this is proved by Boutillier and Ditellier. So they find a measure-preserving correspondence between contours in the XOR Ising model and the level lines of diagonal height functions on the square hexagon lattice. And then the level lines of diagonal height functions on the square hexagon lattice are in bijection with the contours of the constraint percolation model. Then therefore, and moreover, the critical XOR Ising model, its contours has the same distribution as the contours of the constraint percolation measure, satisfying all those conditions, including the strong translation invariant and the ergodicity and the symmetric and the interchanging zeros, ones, and finite energy. However, non-critical XOR Ising model, they satisfy all the conditions except the strong translation invariant. That means the primal contour and dual contour don't have the same distribution. However, in the critical XOR Ising model, the primal contour and dual contour have the same distribution. So those critical Ising model are self-dual. Okay, then we have such a theorem. So then because when we have already shown that for the constraint percolation measure satisfying all those conditions 1 through 5, almost surely there are no infinite clusters and there are no infinite contours, and then we can obtain the same result for the critical XOR Ising model. For the non-critical XOR Ising model, they satisfy all the conditions except that the primal contour and the sim contour, they have different distributions. Okay, and then let's consider PC is the critical probability for the i.i.d. Bernoulli side percolation on the square grid. So although the i.i.d. Bernoulli bound population on the square grid has critical probability PC equals 1/2, so for the critical Bernoulli side population on the square grid, this PC is strictly greater than 1/2. Then therefore we can construct some stochastic domination. Let's say H0 is the positive number obtained from PC by this identity. So by this identity, then we consider a high temperature XOR Ising model on the square grid, satisfying such a condition. Then almost surely there are no infinite plus clusters or infinite negative clusters, and there exists exactly one infinite contour. So let's see. So when JH plus JV is less than H0, then the XOR Ising model is stochastically dominated by a subcritical i.i.d. side population on Z2. Okay, and then, so for the subcritical i.i.d. Bernoulli side population, subcritical i.i.d. Bernoulli side population, there are no infinite plus clusters, no infinite negative clusters, and the mean cluster size is finite. And because the connectivity probability decays to 0 exponentially fast, that means if you have two vertices u and v, and then the probability there is a path joining u and v decays to 0 exponentially fast in the distance of u and v. So probability u and v is joined by a path decays to 0 exponentially fast. Okay. Then this is actually true for all the subcritical Ising side percolation. Then so this is actually true for all the subcritical Ising side population. Then we use the Barak-Contelli lemma. Then we can show that there exists a unique infinite contour because there are no infinite clusters. So then an infinite cluster must be bounded by a contour. But the contour is finite. Then there is some cluster bounded this infinite cluster. Then this cluster is also finite, and there is a contour. If this contour is finite, then there is a cluster. On cluster finite, there's a contour, and this process just go on and on. Then we can use a Barak-Contelli lemma. Okay, so because the connectivity decays exponentially fast, so there exists some contour for a fixed point, the fixed point is in a contour of length sufficiently large, decays exponentially fast. Then there exists such contours. Those are events whose probability we add them up, which is finite. And then by the Barak-Contelli lemma, these events cannot appear infinite often. But we already know there are no infinite plus clusters and no infinite negative clusters, then there must be infinite contours. So this kind of process cannot repeat infinitely many times. So this is how we do the high temperature XOR Ising model. For the low temperature XOR Ising model, we are going to use the duality. So from the high temperature Ising model, we can obtain a low temperature Ising model using those duality configuration by constructing those coupling constant of low temperature XOR Ising model from the coupling constant of high temperature Ising model by those conditions. Okay, then we can show that in the low temperature XOR Ising model, almost surely the total number of infinite plus clusters and the infinite negative clusters, the sum of their numbers is at most 1. Okay, so first of all, the low temperature XOR Ising model cannot have an infinite contour. If it has an infinite contour because of duality, then in the dual high temperature XOR Ising model, there must be an infinite cluster. But in the dual high temperature Ising model, we have already shown that we cannot have infinite cluster. So in the low temperature XOR Ising model, we cannot have infinite contour. Okay, so we cannot have infinite contour. Then, okay, then the constraint percolation, model. Okay, so we assume, okay. Yeah, so the total number of infinite plus clusters and negative clusters in the low temperature XOR Ising model is exactly 1. It's not at most 1. It's exactly 1 almost surely. That's because we have already shown that in a high temperature case, there's an exactly 1 infinite contour. Is exactly 1 infinite contour. Then in the low temperature case, there must be an infinite cluster containing this infinite contour. That's because those low temperature and the high temperature experiments for the Ising model. We get 2 set of contours. One set of contour lives on the primal graph, and 1 set of contour lives on the dual graph, and those contours cannot overlap. One contour is a contour of high temperature model, and the other contour is the contour of low temperature model. If in a high temperature there is exactly 1 infinite contour, and then in the low temperature model there must be an infinite cluster including this infinite contour. So then why there cannot be more than 1 infinite clusters? Because okay, I'm not going to go into the details of this proof, but actually this can be proved using the duality between high temperature Ising model and the low temperature Ising model. So what I'm going to talk about next is this kind of condition, this kind of technique can also generalize to other planar lattices. So we have a degree 4 graph. Each vertex is incident to 4 faces, like faces of degree m, degree 4, faces degree n, and degree 4. So if 1 over m plus 1 over n is 1/2, and then we have a graph which can be embedded into the Euclidean plane. If this 1 over m plus 1 over n is greater than 1/2, then this lattice can be embedded into the sphere, and this lattice is actually a finite lattice. If 1 over m plus 1 over n is less than 1/2, then this lattice can be embedded into the hyperbolic plane, and it is actually a non-amenable graph. So here is an example of 3474 lattice. It's non-amenable, and it can be embedded into the hyperbolic plane. So if we study those percolation on such a lattice, and we require the same kind of constraint around each square face, that means each square face either all the vertices have the same state, or we just divide them this way or divide them that way, such that all the vertices on the same side have the same state. Then we can obtain similar result, because so the major difference between in a percolation on a non-amenable graph and the percolation on an amenable graph, recall that when we consider the percolation on ZD, we have only 1 PC. So when P is less than PC, so i.i.d. Bernoulli percolation bundle aside. So when P is less than PC, almost surely there are no infinite clusters. When P is greater than PC, almost surely there exists exactly 1 infinite cluster. So in the hyperbolic graph, so we consider i.i.d. percolation on the hyperbolic plane. So it is proved that there is not only a PC but also a PU. So when P is between 0 and PC, almost surely there are no infinite cluster. When P is between PC and PU, almost surely there are many infinite clusters. When P is between PU and 1, almost surely there is a unique infinite cluster. So there is an intermediate phase. So basically, what we're going to do is we can generalize this technique to graph embedded into the hyperbolic plane and study those constraint percolation configuration with no assumption of stochastic monotonicity and no assumption of then we can show that in a lot of cases there are infinitely many infinite zero clusters and infinitely many infinite negative clusters. This is also related to the XOR Ising model on this graph because we also have the same duality. We can also have the same duality in the XOR Ising model on such a graph. Because if we choose a finite graph and if we consider an Ising model with free boundary condition and Ising model and the random cluster representation of this Ising model with free boundary conditions and the dual graph and dual configuration is a random cluster configuration with wild boundary condition. And we can similarly apply those duality relation and use the planar duality to obtain that in a lot of cases there are infinitely many infinite plus clusters and infinitely many infinite negative clusters. Some nice results we can obtain is when this m is equal to 3. Because when m equals 3, we can construct those two auxiliary lattice L1 and L2. Those L1 is a triangular lattice, L2 is a regular lattice such that every vertex has degree 3 and every face has degree 7. And then in that triangular lattice, if we consider the contours separating the contours on the dual lattice over triangle lattice. So the contour must satisfy the condition that each vertex has an even number of incident present edges. Then if we have an infinite contour, that infinite contour must be a double infinite self-folding path. This is a very special case because in a lot of cases, if there is a unique contour, then this contour cannot be a double infinite self-folding path because there is a result for the percolation, for the invariant percolation on the non-amenable graph, which says that if there is a unique infinite cluster, then unique infinite cluster, then we consider i.i.d. Bernoulli percolation on that unique infinite cluster. Say i.i.d. percolation on that unique infinite cluster, say S, and the critical percolation probability must be strictly less 1. So if there is a unique infinite cluster and that unique infinite cluster is the infinite path, then we consider the critical population probability for that infinite path. Then that probability must be 1, which is contradiction to this fact. This is why a lot of nice results can be obtained when this m is equal to 3. So that's all I want to talk about.